So now that we know how to find oxidation numbers, we can use those to balance reactions using those oxidation numbers. Okay, so if the oxidation number of an atom or ion changes during the chemical reaction, okay, then we can assume that there's been an electron transfer, and so a redox reaction has occurred. An increase in oxidation number is defined as oxidation. A decrease in oxidation number is defined as reduction, okay, which makes sense. And so if I'm balancing using my oxidation numbers, okay, I'd assign my oxidation numbers for my reaction. So like in this case, carbon is uh, oxygen would be +1, carbon would be -4. Okay, and then over here, like this would be 0. It's just element, and then oxygen's -2, so this is going to be +4, and -2, and +1. Okay, so those would be my oxidation numbers. So carbon is oxidized because it goes from -4 to +4. Okay, so it's increasing in oxidation number. Okay, and then meaning since it's undergoing oxidation, methane is our reducing agent. And then oxygen is going from 0 to -2, so it's being reduced, which means that it is our oxidizing agent. So it's going from 0 to -2. So yeah, that's reducing. The oxidation numbers can then be used to balance a complete reaction. This system is based on the assumption that the number of electrons gained is equal to the number of electrons lost, and the total increase in oxidation numbers must equal a total decrease in oxidation numbers. So I'll do some sample problems for you to balance, show you how to balance. So the first thing, again, what you want to do, write out what the oxidation numbers are. So for this first one, zinc is 0, hydrogen, because it's ion, is +1, same as ion. Zinc, because it's ion, +2, and H2 would be 0. It's just an element. Okay. So our zinc is going from 0 to +2, so it is being oxidized, which means it's our reducing agent. And then hydrogen is going from +1 to 0, so it's being reduced, which means it's our oxidizing agent. Again, in the balance, or for right now, we'll just worry about using to identify oxidation reduction. So that we aren't going to balance yet. This one's actually already balanced for us. Okay, so in this case, again, carbon is 0 because it's just an element. Oxygen 0 because it's an element. And then CO2, the oxygen's -2, meaning carbon has to be +4. So our oxygen is going from 0 to -2, so it's being reduced, meaning it's our oxidizing agent. And then carbon's going from 0 to +4, so it's being oxidized, meaning it's our reducing agent. And this last one, fairly long, but we can get through it. Okay, so again, -2 for oxygen. So that means that we have a -14 charge. We want to end up with a -2. So this needs to be +12 because there's 2 of them. We're going to say each chromium is +6. Hydrogen is the same as the charge here as the hydrogen ion. Oxygen's -2, hydrogen's +1. So we get +6 -2 is +4. And divided by 2, so this has to be a -2 to balance out that charge. Chromium, it's just chromium 3+, so it's +3. Hydrogen, oxygen's -2, hydrogen's +1. This one, again, +1, +1, -2, -2. And again, we have 2 different carbons, so we'll have to split them up equally between the 2. So we have +4 for oxygen, -4 for oxygen, +4 for hydrogen, meaning that our carbons are going to be 0 to balance it. And so now we just look, what's changing numbers? So we're going from +6 to +3, so that's being reduced. It's going down a number. So that means that's our oxidizing agent. And then like hydrogen's +1, over here it's still +1. Carbon's -2, and it's 0. So it is going up in number. So it's being oxidized, which means this is our reducing agent. So from that, we can now use those, like once we know our oxidizing and reducing agents, we're going to use those to kind of balance our numbers. So here's the steps for balancing using oxidation numbers. Okay, so step one, we're going to write our unbalanced reaction. If we aren't given it already, okay, we write down what we have. Like, and so that's where you might have to like write down the entities like you did for a half reaction. So either way. Okay, then you're going to assign oxidation numbers to each atom in the equation to determine whether it is a redox reaction. So that's, again, if you don't have a change in oxidation numbers, it's not a redox reaction. All of the ones we did in the last example all change, and so we can find our oxidizing and reducing agents. If the redox reaction, if the reaction is a redox reaction, identify the atom or atoms undergoing an increase in oxidation number, and the atoms are undergoing a decrease. So basically, you find out what's our oxidation reaction, what's our reduction, and what's our oxidizing agent, reducing agent. Then we're going to find the numerical values of increase and decrease in the oxidation numbers. Okay, so basically, how much are they going up, how much are they going down? Determine the lowest common multiple of electrons lost by the reducing agent, and that's the one that increases in oxidation number, and the number of electrons gained by the oxidizing agent, so the decrease in oxidation number. Apply the numbers found in step 5 to balance the number of atoms oxidized and the number of atoms reduced. Balance the other elements by inspection if possible. Okay, and then for the reactions that occur in acidic or basic solutions, we're just going to worry about acidic. Okay, include water molecules and hydrogen ions. We don't have to worry about the hydroxide ions. All right, so here's an example using those steps. Okay, so we're already given, like, we're past step 1, okay, because we have our unbalanced equation that's given to us here. So step 2, we're going to assign oxidation numbers to everything in there. So again, for this first one, like we'd look at what's more electronegative is sulfur, it's -2, meaning that silver has to be +1. Aluminum's on its own, so it's 0. Now -2, and aluminum's going to be +3 in that compound, and then silver on its own is 0. Okay, so silver is going from +1 to 0, so it's being reduced, meaning it's our oxidizing agent. And then aluminum is going from 0 to +3, so it's being oxidized, and it's our reducing agent. Okay, so now that we have that, we want to see how many electrons are changing. So silver is going from +1 to 0, so there's 1 electron transfer per silver. Okay, but if we look here, we have 2 silvers. Oh, sorry. 2 silvers. So I'm going to have 2 electrons transferred per Ag2S. And then for aluminum, there's 3 electrons transferred per aluminum. And because, we just have 1 aluminum here, we have 3 electrons transferred for aluminum. So like our compound, that's fine. And it has to be the reactant. We aren't worried that there's 2 over here. We'll worry about that later. Okay, so now we want to balance out our electrons. So we have 2 over here, 3 here. So our common multiple, we're going to times everything by 2 over here and times by 3 over here. Whatever we times it by, that becomes our coefficient. So this number comes up here, and we get a 2, and this number comes up here, and we get a 3. Now, if we look here, so we got all that. So now balance other elements by inspection. So we're just now looking to see if everything's balanced. So we have 6 silvers, so we need to put a 6 over here. We have 2 aluminums, We have 2 aluminums, those are balanced. We have 3 sulfurs, those are balanced. And yes, I know you could probably balance this one just by looking at it without doing all this extra, but uh, when we get into actual tougher ones, larger ones, then it's a lot easier to write this out, do it this way. So this example here, it's kind of broken down the steps. We're just going to kind of do it all at once. We'll use this one down here. Okay, but it says, yeah, like use oxidation numbers. So we're going to assign the oxidation numbers to start. So again, hydrogen's +1. So sulfur has to be -2. Oxygen 0. Over there, it's -2, meaning this has to be +4. And -2 and +1. Okay, so now we have them. Okay, we decide, we see what's being oxidized and what's reduced. So sulfur is going from -2, whoops, to +4. So it is increasing, it's being oxidized. So it's our reducing agent. And then oxygen is going from 0 to -2. So it's our oxidizing agent. Okay, now we look and see what the change is. I'll write it up here just so we can see. So under H2S, I have, it's going from -2 to +4. So we have a 6 electron transfer per sulfur because there's just one sulfur in our compound. Okay, we have 6 electron transfer per H2S. And then for oxygen, we have a 2 electron transfer per oxygen because there's 2 of them. We have 4 electron transfer per O2. Okay, what's our common multiple between 6 and 4 would be 12. So we're going to times everything in this by 2 and times everything in this by 3. So then again, that becomes our coefficient. So this is going to be a 3. This is going to be a 2. Okay, now once we have the coefficients for reactants, so that's kind of this step here. We wrote it down here. Okay, now we just start scanning through and looking to see. So we have 4 hydrogens. We need a 2 over here to balance that out. We have 2 sulfurs, so we're going to need a 2 here to balance that. And then we have 6 oxygens. Over here we have 4 plus 2 is 6. So now we have a balanced reaction.